Hello everyone, so this week we're going to talk about cryptography. So this is covering chapter 12 in your textbook, and we're going to talk about some of the history and principles of cryptography. We're going to talk about symmetric and asymmetric algorithms, PKI, attacks on crypto systems, and then look at some hashing algorithms and why that's important for data integrity checks. All right, so what is cryptography? It's the study and the process of taking regular plain text, like what you're seeing on the screen here, and converting it into ciphertext. What is ciphertext? It is some form, it can take many forms, of encrypted or unreadable text to send between two parties or between multiple parties. And it's used to hide data from unauthorized users, so to keep data confidential. Decryption, so encryption is the process of converting text into ciphertext, and decryption is the process of taking ciphertext and converting it back into plain text. It's been around for thousands of years. A lot of encryption. I mean, basically, substitution algorithm, for instance, like replacing a letter A with a letter O. This stuff has been around forever. The Caesar cipher is a great example. Looking at keys, essentially, the concept of a key is to unlock something. A key is used to both encrypt and decrypt text. Cryptanalysis is the study of breaking encryption algorithms. Every time a new algorithm is developed, it's studied to see how difficult it is to break it. Essentially, everything can be broken. The question is practicality. If it's going to take you 2 million years to break the encryption, obviously it's going to be a good encryption algorithm, because it's absolutely impractical based on either current or foreseen technologies to break that in a reasonable amount of time. Even within someone's lifetime is probably not reasonable, because by that time the data is most likely useless. The Enigma machine is a great example. It's a very famous encryption device used in World War II that was broken. Essentially, Enigma substituted each letter typed by an operator through a number of rotors in the background. And it was broken eventually, and the machine was called the Bomba for breaking that code. Purple was developed by the Japanese in World War II, and it was broken by U.S. cryptanalysis folks. William Frederick Friedman was the person who did that. There's also the concept of steganography. Again, it's security by obscurity, usually including encryption as well. So taking data, hiding it within pictures, oftentimes that data is also encrypted. You can think of it almost like a digital dead drop. Encryption algorithms are the actual function that's used. You pass a key in and your plain text, and it will output ciphertext, and oftentimes you'll have the option to do it in reverse. The key is a sequence of random bits generated from allowable values. Oftentimes you have a seed value as well. The bigger the key space, and it's not just the bigger the key, the more of the key that the encryption algorithm uses for generating the encrypted ciphertext, the more random sequenced, the more difficult it is to guess that encryption. So here's an example of a random selection. Now there's a few basic algorithms. So symmetric is where you use a single key, a single password to both encrypt and decrypt. But then you have asymmetric algorithms where you have two separate keys, one which will encrypt data and one that will decrypt data. This is the concept of PKI, or public key cryptography. This is what's used in certificates. And then hashing, essentially, it's creating a unique identifier for a set of variable length data. Now, again, you could variable length data, you can think it has an infinite number of possibilities. It could be anything from a book to an MP3 file. A hashing algorithm takes that and within a specific set of bits creates a unique identifier. Now, obviously, as the sample set goes towards infinite number of possibilities, and you're trying to reduce that down, you end up with what's called collisions, where you have two different hashes that could match two different things. So you have to be careful. You want to pick a good algorithm. You want to pick a long enough hashing result that you can avoid collisions as much as possible. The advantages to symmetric algorithms, they're faster, they're difficult to break, but the biggest problem is how do you share that secret? That key is that secret, and it's an issue of trust, right? How do you deliver the keys without theft? How do you ensure that every party who has the key doesn't divulge the key? So this goes into non-repudiation and authenticity issues. Stream ciphers and block ciphers are the biggest types of symmetric algorithms. DES, the data encryption standard. Version 1 of DES definitely not used anymore, but it was created by NIST, and they wanted a means of protecting sensitive but unclassed information. And they allowed vendors to submit various algorithms. IBM proposed the Lucifer algorithm. It's a 128-bit encryption algorithm, and it was used to create DEA after NSA reduced the key size to 64 bits. In '88, the NSA thought that standard was obviously too weak, and this goes to, when we talk about practicality issues, as the power of computers, the power of processing goes up, we talk about Moore's law, as quantum computers are being developed, these things become practical. So this is why you have to be forward-looking when you generate encryption algorithms. So obviously in '88, the NSA took the DEA and decided they needed to upgrade it. Triple DES was kind of a quick fix for DES vulnerabilities, but it took a lot longer, but it was stronger than the original standard. Advanced in AES, you've probably heard of. This is the newer encryption standard. There were 5 finalists. Rindale was the winner, but you've probably heard of Twofish and Serpent as well, RC6, and Mars. The international data encryption algorithm is also a block cipher. Works on 64-bit blocks with a 128-bit key. It's really designed for computers with less computing power and is free for commercial use. Blowfish is 64-bit blocks as well, but also a key length of up to 448 bits, and that was developed by Bruce Shiner. And RC4 is a stream cipher that was used in WEP. It's super simple to break. RC5 is a block cipher, but you can use a key size up to 2048 bits. Asymmetric algorithms are a bit different. Again, with symmetric algorithms, you have to worry about key sharing, secrecy. But with asymmetric algorithms, you have 2 keys. They're mathematically related, but only one can encrypt and only one can decrypt. And this is your public key and private key. It provides authenticity and non-repudiation. So again, it'll validate a sender, and the sender cannot deny sending the message. But obviously it doesn't offer the confidentiality portion that the symmetric algorithms do. So how does it work? If both you and I want to send a message, I encrypt the message with my private key, and out in the open is my public key, and you can grab that. Anyone can grab that. And you decrypt the message with my public key. We can add confidentiality if we both use a public key and private key pair. So that can be added in, but again, it's not as efficient as a symmetric algorithm. RSA was really the first one using this. This is what the TLS protocol is based off of in browsers, and it's a one-way function to generate the key. Diffie-Hellman is another example. It is an algorithm that's used to establish a secret key between two parties. So each party generates a shared key under a key agreement, and they share it with each other. Now the problem again is if the key is intercepted during transmission, it throws everything out the window. Elliptic curve cryptography was really built for low power devices. You wanted to perform asymmetric algorithms on an IoT device. You can't use some of the other algorithms. So ECC was created for that. And essentially it uses the points on an ellipse to determine various keys that can be generated. El-Gamal, this is used to generate keys, encrypt data. It uses discrete logarithms, but the problem is, the good thing is if you're trying to solve it, it can take many years to break. So again, this goes back to it's not worth your time and effort to try and break it. Again, digital signatures, when we talk about public key infrastructure, this is using asymmetric algorithms. So when we talk about SSL, this is asymmetric. So here's an example of digital signatures. So the digital signature standard was established by NIST in 1991, and it provided a mechanism for verification. RSA and DSA have to be used for all signatures, and the hashing algorithm was SHA, or the secure hash algorithm. PGP you've probably heard of. Oftentimes used for mail, developed by Phil Zimmerman. It's very difficult to break. It uses certificates similar to PKI, but it's decentralized. But the verification of a certificate authority is not as efficient as PKI. PGP supports various algorithms: AES, IDEA, RSA, DSA, and SHA. SMIME, or Secure Multipurpose Internet Mail Extension, is another public key encryption standard, and it's used to sign email as well, like PGP. It can encrypt and digitally sign email and encrypt email messages with attachments. It uses PKI search for authentication, and it's built into Outlook. Sensitive data encryption. You should make it a policy when you need to have secure communication. You have to look at authenticity, confidentiality, non-repudiation, and determine what type of algorithm is good for you. How do you need to encrypt data? Do you need to encrypt it at rest, in motion? What's important? And this goes back to, as you're investigating a system, doing footprinting, designing a system, whatever you're doing, you have to ask the questions of what data is sensitive, what's not, perform a risk register, and then encrypt what you need to encrypt. Hashing algorithms, when we talk about integrity of a file, has a file been modified, has data been modified, that's a really good use of hashing algorithms. So you can take a variable length message, as I talked about before, and you produce a fixed length identifier, almost like a fingerprint. If the message changes, the hash value changes. But because you're taking an infinite set and then moving it to a finite set, you have what are called collisions, where two completely different messages could produce the same hash value. And a good hashing algorithm is collision-free, but There's no such thing. Again, when you go from an infinite set to a finite set, you always have collisions. So you want to reduce the amount of collisions. You've probably heard of MD5, SHA-1 and 2, but here is the basic kind of history of hashing algorithms. When we look at public key infrastructure, the structure is a bunch of programs and protocols and security protocols that use public key cryptography. So you've heard of most of these components, but let's talk about them. So a certificate, it verifies the identity of a specific entity talking to another entity. And public keys are issued by what's called a certification authority, a certificate authority. And that CA binds the public key to the recipient's private key. And each certificate has a period of validity. So when you generate the certificate, it doesn't last forever. You have to renew it. You have to provide your credentials to the certificate authority to validate it. And a CA can suspend or revoke a certificate. Now remember, a CA could be a public CA where anybody can apply and that CA manages certificates for the world, or even an individual company, organization, or you could run your own private CA. So a certificate, whether it's public or private, can be suspended or revoked if an individual no longer meets the criteria. So in a private case, if user leaves a company, if the private key is lost or compromised, if the company no longer exists, or never renewed, the certificates can be revoked. And these revocation lists are available, so if you're presented with a certificate, you or your application could check against this revocation list and see if their certificate is still valid or not. And here we go, the CRL, certificate revocation list, it's all revoked and suspended certificates. A suspension is better than a revocation because, again, let's say you didn't renew or didn't make a payment. It's not a complete revocation, but it stops working for a while. It goes on the CRL, but it can come off the CRL. Once a certificate is revoked, it's revoked forever. HTTP STS, so Strict Transport Security, is created in 2012 for web servers to tell clients they require secure communication. It forces all traffic between a web browser and a web server to be sent over a secure channel. So if the web server's secure certificate can't be validated by the browser is going to block access to the website. And here's an example of the HSTS server header field. So it's very important that you properly back up your keys, even print them off. If the key is lost, destroyed, or compromised, the certificate is no longer invalid. And usually certification authorities or certificate authorities are responsible for backing up keys, but you should do it as well. Microsoft's root CA gives you features in its server OS for configuring a server for being a CA instead of using a third-party CA. And you can add a role in the Add Roles wizard for ADCS or Active Directory Certificate Services. And here's an example of adding ADCS in the Add Roles wizard. If you're selecting a role service to install, here's where you would do it. This is how you specify the CA type, either root or subordinate. And this is how to configure crypto settings for a specific certification authority. All right, when we look at cryptography attacks, you either have passive or active attacks. So passive attacks involve using tools to eavesdrop or perform port scanning, and active attacks attempt to determine what that secret key is to encrypt plain text or decrypt text. The culprit and the general public usually know the algorithm, right? The algorithms are generally public. There's some commercial algorithms that are proprietary, but for the most part, you can figure out what the specific math in the algorithm is. The issue is, if you don't know the key, you can't decrypt, for the most part, unless you find a vulnerability within the algorithm itself. A birthday attack. So if you've ever studied discrete math or enjoy math games, you know that when you talk about probabilities, when you get 23 people in a room, there's a 50% chance that 2 people in that room will share the same birthday. And that, again, just has to do with looking at the statistics of every day of the year, the number of people, where they fall on their birthdays. And there is a similar attack called a birthday attack, which attempts to find collisions. Again, when you take an infinite set of data and you move to a finite set, you have a higher and higher probability that you're going to find 2 disparate sets of data that have the same hash. Birthday attack, it's the same concept. So, for instance, if you have a 160-bit key, you would have to perform 2 to the 63rd power computations to perform a collision. A mathematical attack is where the actual math in the algorithm is used to try and find a weak point or a weakness where you don't necessarily need the key, or you can use a master key to encrypt or decrypt text. So ciphertext only attack, known plaintext attack, chosen plaintext attack, chosen ciphertext attack, and side channel attack are kind of the categories. Side channel attack is usually the most common. You're trying to find a backdoor into figuring out what this is. So again, ciphertext only attack is you have the ciphertext, but you don't have the plaintext. Known plaintext is you know what the original message is. You're going to try and find an attack based on that. Chosen plaintext and chosen ciphertext is you have the ability to choose various plaintext and ciphertext to use that and run it through the algorithm. But side channel attack usually is the way people go because you're trying to find a weakness where you can bypass the key altogether. A brute force attack is where you're trying everything within a key space. So if my key is 1 character, I have 26 chances. Let's say it's 1 lowercase character. I'm going to try A through Z, all lowercase, and one of them is going to work. But the problem is as soon as you add, let's say now we have a key it's just like looking at password search spaces. If I have a 4-digit PIN code, it's 10 to the 4th power possibilities, 10 times 10 times 10 times 10. So you have to look at what's called the search space when you're looking at a brute force attack to determine the number of computations it's going to take you to try every possible key. Man in the middle attack kind of throws the baby out with the bathwater. You are sitting in between the operator and the algorithm, or the computer and the server, and you're just siphoning off data. And you get the key, you get the encrypted text, you get the ciphertext, and the plain text. You can do whatever you want with it. If you are successfully able to perform a man in the middle attack, you don't have to do any of the other cryptographic attacks. SSL downgrade attack is if you can force a server or a browser to use an older, known compromised version of an encryption algorithm with a weaker cipher, you can easily take control using known attacks. Dictionary attack, that's essentially saying people are not the smartest in the bunch. You know that 1, 2, 3, 4, 5, 6 is in the top 20 used passwords. So you can just take a guess. I pretty much know people are lazy when it comes to generating passcodes and keys. I'm just going to guess the most common one. Who's using the word password as their password? So that's a dictionary attack. And a lot of times you can have a rainbow table. So you have, for instance, if you're using hashing algorithms or salted hashes, you know the salt, and you know what hashing algorithm they use. You pre-salt, pre-hash those lists of known words, and then you apply that against the server or the algorithm. A replay attack, similar to man in the middle, you're getting access to data, but essentially what you're doing is you're capturing the data of a session and rerunning it. Password cracking is illegal in the United States. You can crack your own password though. Always be careful. Always ask a lawyer. If a password uses common dictionary words, this is where you can use dictionary attacks and rainbow tables. And you have to obtain the password file from the system first. And in Unix systems, it's etc shadow. That's the file. And in Windows, there is stored in the registry and files as well. Various password cracking tools: Hashcat, John the Ripper, Offcrack, Accept, Loftcrack, and Password Dump 7. Here's an example of running John the Ripper with your own input file. And here's the various parameters for John the Ripper. All right, what did we talk about? Cryptography has been around pretty much forever, ever since people were trying to hide stuff from other people. Ciphertext, that's the data that's been encrypted. Plain text is the unencrypted text. Remember, symmetric cryptography, forward and back, uses the same. Just think of symmetry. Uses one key, where asymmetric encryption uses one key to encrypt and a different key to decrypt. RISA, ECC, and Algol. Again, these are one-way functions to generate a key. They're used in asymmetric encryption. And DSS is the digital signature standard. It ensures that digital signatures can be verified. OpenPGP is a free public key encryption standard. Hashing algorithms are used to verify data integrity, but remember the consequences of collisions, and that's what people search for. Public key infrastructure, that's the structure of the various servers, components, and software that are used to encrypt data, and that deals with asymmetric algorithms. Your digital certificate binds a public key to an owner, and that's issued by an authority. And we talked about active and passive attacks, so attempts to either determine the key or to look for various side channel and algorithmic attacks to gain access to an encryption system.